Hey guys, I am Gautam and welcome to GChemics. So in this video, I will be talking about the Bohr theory of hydrogen and hydrogen-like atoms. So this is a very important topic, and in the last video, I have talked about the fundamental particles. The syllabus I am covering here is the IIT chemistry syllabus. So today, I will be discussing about the Bohr theory, okay, and a lot of other things regarding the Bohr theory, okay. So what we will learn, those are like how Bohr theory came. I will be talking about the story before the Bohr theory came, what was happening at the time in the scientific community. I will be talking at the story, okay, so that you get a little bit interest in that. Then how to get the Rydberg equations, how to analyze spectral lines, what about alpha, beta, gamma spectral lines, how to nomenclature that, how to get everything. What is the atomic model, okay, according to Bohr theory, merits and demerits of Bohr theory, what was the drawbacks and what was the plus points of Bohr theory, correction, what are the correction needed in the Bohr theory, how to get ionization potential. So this topic is very important because a question came like directly from ionization potential, that the concept was in Bohr theory, but the question came in IIT JAM exam. I don't know the year, but it's maybe 2015 or 16, like that. Then what is Bohr correspondence principle? This is like higher quantum mechanics like things, okay, so that is quite interesting and very easy. And finally the atomic units. So first, how Bohr theory came. So there was an experiment like an electrical discharge, okay, so there was a tube, okay, there was a tube, and in that tube, in that electrical discharge tube, low pressure hydrogen gas was present, and at that tube we incorporate the electrical discharge, okay, which was passed through that tube. So when we do that, we got, the scientific community got the spectral lines of ultraviolet, visible and infrared region. So they got some kind of spectral line, but the problem was they did not explain the spectral lines, that why we are getting these spectral lines. Okay, so those are called the emission spectrum of hydrogen atom. Why it is emission spectrum? Because it releases energy, and with that energy we are getting those spectral lines. If it absorbs energy, then we call it absorption spectrum, but here it is emission spectrum because the system releases a lot of energy. So this looks like that you will get to see a lot of lightning effect, okay. So this kind of emission spectrum in the UV visible and IR region they got. So they could not explain the whole things, okay. So to explain those things, three formulas came. First was Bohr formula, second was Rydberg formula, and third was Reed's combination formula. So what was those? What were those? So let's talk about Bohr formula. So we can explain the Bohr formula by considering this equation, okay. Bohr derived this equation from experimental results, and in this equation we can get the lambda, that is wavelength, and this wavelength is for each line, right? So for each line we are getting the wavelength, and this is a constant, and this is n, that is an integer which has value 3, 4, 5, 6. I am telling you that why it starts from 3. So look at 4. So don't see as it as 4. It's okay, you have to see it as 2 square. Okay, and you know already that for Bohr series you have to get Lyman then Bohr. That means anything that is 2. Okay, for emission spectrum, every electron need to come to second orbit. That is n equals to 2. That's why it's Bohr formula. Okay, so here n, if any 2 square, that means n should be more than 2. That's why it starts from 3, 4. That is, it need to come from 3 or 4 or 5th orbit in the second orbit, right? So that's why so k is a constant which has value 364.6 nanometer. So this is called Bohr series at that time, and here it is alpha. 3 means alpha, 4 means beta, 5 means gamma. So I will be talking about this a little bit later, but let's talk about the next series, that is about Rydberg equation, Rydberg formula. So you know about Rydberg formula, but for the first time the Rydberg equation was derived, the formula looks like that, okay. And here, you know, from the modern concept, that here it should be multiplied with something, but you know the actual formula where z square need to be multiplied. But here we don't know about that. At that time, Rydberg didn't know that what was that. So he just told the scientific community that something will be multiplied to the other terms. Okay. So what was that something? At that time, they didn't know, or Rydberg didn't know. Here also, this is also for Bohr series. Okay, Rydberg, this formula is also Bohr series. That is here also 2 is present. So that's why n values has values 3, 4, 5, 6 like that. Similarly, then come a more general formula, which was the Reed's combination formula, Reed's combination principle, which looks like that, this equation. Okay, so here listen. In the last formula, we got that we need to multiply something to get the exact 1 by lambda or nu bar, that is called Webb number, nu bar, that is equals to 1 by lambda. To get this value, we have to multiply something with these terms. Here in the Reed's combination, we did not get that something. So what we did, that means that something do something so that we get the exact nu bar value. So here we that term is not incorporated. Okay, so that's why here alpha and beta, two other terms are incorporated, and alpha and beta are called adjustment constants. That means what these something terms did there, here alpha and beta does the same. Okay, so alpha and beta, these are called adjustment constant. And if we talk about different elements for hydrogen, helium, lithium, anything, so for different elements, we will get the different alpha and beta values. Okay, so that's why alpha and beta are dependent nature of the elements. That's why we will get different spectra for different elements. Okay, so that's why alpha and beta, those just adjust the nu bar value. Okay, based on the experimental value. Okay. But the problem was this is more general formula, because if we get the alpha and beta values, then you can explain this kind of all the series, Lyman, Balmer, Paschen, Brackett, Fund, then the corresponding spectral region where we can see these spectra, this series, m and n values, then that you can know that if m equals to 1, n should be more than 1, 2 more than 3, so different series. So this you know already. Okay, so I am not getting into that, but I am not going into that. But let me talk about first one, that if from second, third or fourth orbit, if it comes to one orbit, so I cannot, listen one thing, I cannot use the word orbit, because at that time atom was not discovered, so there was no concept like orbit. So that's why I don't know what to use that, what we can use that, but let's talk about anything. Okay, but let's m and n value. So putting different m and n values, we can get the lambda or wavelength, Webb number values, right? And you know that for hydrogen atom, if we talk about that something, so here it is z square from the modern formula, modern Rydberg equation. So for hydrogen atom, z should be 1, so that something vanishes. So for hydrogen atom, here also, if that something vanishes, so here also alpha and beta should be vanished. That's why alpha and beta will be 0 in case of hydrogen atom. Okay, then other terms will be valid. So we will get different spectral series, right? So now at the time another experiment was done, that was the Rutherford's nuclear atom model, and there was an experiment like there is a alpha particle source. Okay, and with that source we shine alpha particle beam light to the gold foil. Okay, so when we do that, we get different deflection. Okay, so the first one is some of the radiation comes back, some of the radiation passes through the gold foil, and some of the radiation it changes its direction. So why is that? So based on that experiment, okay, this is called Rutherford's nuclear atom model. Based on that experiment, we get to know this is the alpha particle beam. So you know the alpha particle is helium 2 plus, positively charged particle. That's why when it collides with the gold foil, that means gold foil makes up gold atom. Okay, and as it comes back, that means this is positively charged, that should be positively charged. Something in the gold atom, there should be some area where positively charged particles are there. That's why the positively this Rutherford got to know that in the atom there is a positive region. Okay, and some of the radiation passes through the gold foil. That means in gold atom there was an area where nothing present. That means in the atom a lot of vacancy are there. Okay, so this radiation means that. Okay, mean that, and in some cases this kind of direction changing is occurring. That means in the atom there is a region where the oppositely charged particles are present. As the oppositely charged particles are present, so this beam collides with that particle, and that's why it, after colliding, it just changes its direction. So here we are getting two parts. First one is nucleus, where positively charged particles are there, and second one is the nuclear electronic part. And there was a vacancy, a lot of vacancy in the atom. Okay, so we got these from this alpha particle radiation in an experiment. We got this atomic model. But Rutherford postulated that in an atom, electrons are continuously radiates its energy. That's why if it continuously radiates its energy, so its energy will be decreased, and finally it will vanish. It will come to the nucleus and it will vanish. Okay, so that's why it gets vanished at some point of time. But if it occurs, then we should get two things. We should get continuous spectrum, as it continuously releasing its energy, and the second thing is it cannot explain the stability of an atom. Okay, so that was the problem at that time. So that's why Rutherford model was not succeeded, but it gave the idea about how a atom may look like. Okay, so next what happened in 1913, Bohr gave another model that was based on old quantum theory. So we have entered into the quantum theory. So why old quantum theory and what was the new quantum theory? So we need to know that. So old quantum theory means the quantum theory where both classical mechanics and quantum mechanics are involved. So in the Bohr model, we need to consider both classical mechanics and quantum mechanics. Okay. So in the future we will get to know what about quantum mechanics, what are the quantum mechanical postulates, things like that. But now you know about the classical mechanics. So in Bohr theory, some kind of classical mechanics are involved. That's why Bohr theory is a product of old quantum theory, right? And in this video and in this section and in IIT JAM syllabus or in graduation level, we just consider the hydrogen or hydrogen-like systems, that is one electron systems. Hydrogen-like system means helium plus, lithium 2 plus, where only one electron is present, right? So here the postulates of Bohr theory are the first one. Okay, so before that, let me talk about the atomic model that Bohr was suggested. Okay, Bohr suggested. So the atomic model was like, there is a positive region, as Rutherford said that there is a positive region and the electrons are revolving around the nucleus in a circular way. But the problem is, the thing is that when electron is revolving at that around the nucleus, they don't release any kind of energy. But Rutherford said it always releases energy and finally it crashes onto the nucleus. Okay, but Bohr said no. When it revolves around the nucleus, it doesn't release any kind of energy. So when it releases energy when it jumps from one orbit to another orbit. Okay, one higher energy orbit to one lower energy orbit. So remember this one, from the nucleus, if the distance increases, then the energy of the orbit also increases. Okay, so that's why for n equals to 1 orbit, the energy will be lower than the n equals to 2 orbit, and n equals to 3 orbit we will have higher energy than 2 or 1. Okay, so energy generally increases if the distance from the nucleus is increases. So when a electron jumps from n equals to 3 orbit to n equals to 2 second orbit, okay, so when it should release some kind of energy, and that energy will be equal to h nu. Okay, so the energy difference should be h nu. And when you change the energy, when you want to calculate the energy difference, so you need to subtract the lower energy value from the higher energy value. That means you need to subtract the n equals to 2 value from n equals to 3 energy value. Okay, so now let's talk about different postulates. The first one was mvr equals to nh by 2 pi. So what is mvr? Mvr is the angular momentum. So as electrons are revolving in the circular path, okay, so it should have angular momentum, not the linear momentum, that is mv, but here angular momentum. So what is the r here? The distance of the orbit where the electron is revolving. Okay, and that will be equal to h by 2 pi and some integer. Okay, Bohr did not explain the significance of n. Okay, the integer. So h is, you know, that Planck's constant. Okay, so that was Bohr's first postulate. The second was each of the orbit, okay, which are stationary, which are in stationary state. So what does it mean by stationary state? That means each orbit should have a fixed amount of energy. Okay, it doesn't release, it doesn't emit any kind of energy when electrons are revolving in these orbit. Okay, so every orbital should have a particular energy state. Okay, and at that energy state a particular amount of energy is present. So that is called, those energy states are called stationary states. So for each orbital we will get one stationary state. The third one, I have told you that the energy of final minus initial. So final will be higher energy value, initial will be lower energy value. So from n equals to 3 to n equals to 2, that is n equals to 3 should be higher, n equals to 3 should be higher energy value and n equals to 2 should be lower energy value. So you have to subtract 3 to 2. Okay, so E3 minus E2, that will be equals to h nu, as I have told you. Okay, so this amount of energy will be released by the system when electron comes from third to second orbit. Okay, and remember one more thing, that electron can jump from 3 to second orbit, but electron cannot stay in between this state. So that's why the Bohr theory is quantized. Okay, the or energy level, each orbit is quantized. So what does it mean, the word quantized? Quantized mean there should have some energy level. Okay, here is not energy, here it's the stationary states, or here is the different orbits. So each orbit should have a particular amount of energy, and electrons will be present in those orbits. Not electrons cannot be present in between two orbits or like that. Electron can be in n equals to 3 orbit, electrons can be in n equals to 2 orbit, but electrons cannot be presented in between the two states. Okay, so that's why a particular energy levels are there, and in those energy levels electrons can only be present. Okay, so that's why those states are quantized. That is quantization. So I'm sorry. So the last and final postulate was that quantum Bohr's atomic model that follows some classical laws, like when electrons are revolving around the nucleus. So we have to consider the equation. We have to consider the formula of revolving, like when we use the formula, like when Earth is revolving around the sun. So the formula we are using here, we have to use the same formula when electrons are revolving here. So that means we can use some classical laws to develop this Bohr atomic model. That's why, and like Coulomb's law of attraction, centrifugal force, yes, these all are the classical laws. So Bohr's atomic model follows the classical laws. Okay, that's why Bohr's atomic model, because the theory of quantization, that is a quantum mechanical concept. Okay, and the theory of revolving the electron, Coulombic force of attraction, centrifugal force, these are the classical mechanical concepts. That's why Bohr's atomic model is old quantum theory, is a product of old quantum theory, right? So let's see different calculations regarding the same. So let's have a look at this picture. So this is the nucleus and this is the orbit. So here there is an electron whose charge is E. The mass of the electron is V. The velocity of the electron in this orbit is V. The distance from the nucleus of this orbit is R, and the charge of the nucleus is Z into A. So why Z? Z is the number of proton. That means neutron is neutral. That's why as neutron is neutral, that's why the total charge will be number of proton multiplied by charge of the electron. So the opposite charge of this. So for hydrogen-like system, there will be only one electron. So one electron and this number of protons, that is charge. So according to Coulomb's law, this negatively charged particle will be attracted by this positively charged nucleus. So the force of attraction, that is called Coulombic force. So to be stable, the system need to have some outward force, okay, that is called centrifugal force, as it is revolving, okay. So this Coulombic attraction will be equal to the centrifugal force to make the system stable. That's what I have done. So in SI we need to multiply this one, and according to Coulomb's law, this charge multiplied by this electron's charge divided by distance square. So we have written that formula, and then the centrifugal force, that is mv square by r. So I am using Rn or Vn like that. That means n is the nth orbit. So here it's the first orbit, so n equals to 1, the first orbit, right? So first orbit n equals to 1. For the second orbit, the radius will be different, okay, velocity may be different, so that will be second orbit v1, v2, r1, r2 like that. So that's why I am using Rn or Vn. Then after organizing this equation, okay, so we are getting like Rn equals to this, okay. So you can just pause the video and do the calculations, because nothing is tough over here. So after getting this Rn equation, there is a Vn term, okay. So we have to put the value of Vn square. So from postulates of Bohr theory, we get the mvr equals to nh by 2 pi. So we need to use that one. So mvn rn, I have used vn rn equals to nh by 2 pi. So we get Vn equals to this, and as we have to put the value of Vn square, so we have to calculate the value of Vn square. So we have squared the both sides. So we are getting this one. So after getting this one, just put the value over here, okay. Then you will get the equation of this. So after organizing that, I will be getting this equation, which is in SI, as we are using 4 pi epsilon naught value, right? So if we omit this value, then in the CGS unit, the equation will be this radius equation for nth orbit, okay. And you know that in the CGS unit, 4 pi epsilon naught has the value of 1. So now we have already got the radius, that is the distance from the nucleus, distance of the orbit from the nucleus, okay. For any orbit, for R1 we can put n equals to 1, for R2 we can put n equals to 2, for any other nucleus like helium plus, that is also one electron system. So first helium plus, for the first one, that is R1, here put 1, here put 1, but you have to put Z equals to 2, because the number of proton is 2 in helium. So that's how you can calculate a lot of values, the radius values of every one electron system. Now let's calculate the energy of an atom, okay. So total energy will be the total kinetic energy plus potential energy. So from the classical mechanics, you know that total kinetic energy is half mv square. So for nth orbit, Vn is half mvn square, and the total potential energy will be, listen, how to get the potential energy. So there is a nucleus and there is electron. So what is potential energy? So to get the potential energy value, what we need to do, we need to incorporate a concept like, suppose the one electron is present at infinity. So to bring that electron from infinity to at a radius r, we need to do some work, and you know that work equals to force multiplied by displacement, right? So that's why the work done in that section, so there is electron and it is a positively charged nucleus, so the force of attraction will be Coulombic force of attraction. So that's why I have used Coulombic force, and along with the force I have multiplied the displacement drn, okay. So and we have to bring that electron from infinity to r, so we have used the integration term. So after doing that integration, okay, we will get this value, and the negative charge is for that, you know that we from infinity to bring an electron from infinity to radius r, we need to do some work by the system, because the system will do work to bring that electron at a distance of r. So as system is doing the work, so there is a negative charge, okay. So this negative charge implies that one. Or after getting, so I have got this value, okay, after just doing the normal calculation, and from if we put the value of Vn, so let me show you the value of Vn square. So put that value Vn square over here, okay. So you will get this equation, this value. So after doing the calculation, you will get this one. So here these negative charge implies that the work need to be done by the system. As system is doing work, so that's why this is the negative charge. Okay. So we are getting that total energy En for different energy orbit. Okay. So total energy will be this. There is the Rn. So we need to put the value of Rn from this equation. Okay. This Rn value. So putting the Rn value over here, we will get this equation, energy value, this one. Don't look at this. Okay, just look at that part. This is the part of in SI unit, and this is the energy in CGS unit. Okay, so how to get CGS SI? So just if you want to calculate the value in CGS unit, don't put 4 pi epsilon naught. You will get the value in CGS unit. Then do the calculation. You will get the energy equation in the CGS unit. So here 1. Remember, here I am in this video. I am using 1 that implies the hydrogen atom. So for hydrogen atom, Z equals to 1. So putting or ignoring Z value, both are same because Z equals to 1. So just only variable is N square. Okay, for hydrogen atom only. Okay, so for CGSSI only for hydrogen atom, this is true. So if you ignore the Z value, then after putting AM, E, 8 epsilon naught A square, all those values, you will get some energy value. Okay, and if you put Z value equals to 1, so except N value, that is N varies for first orbit, second orbit, third orbit, so it's a variable. So if you put the value, then you will get the except N, you will get the value for hydrogen atom. So that energy will be E1, that means the first orbit of hydrogen atom. So if you are interested in getting the energy for different other orbits, so if you need to calculate the value of 2. Okay, so for first orbit N equals to 1, Z equals to 1 because it's hydrogen atom. So if you need to calculate the energy of second orbit, that is E2, that will be equals to E1 divided by N square. Okay, because N is the variable over here, because the Z value will be 1 for hydrogen atom. But if you want to calculate for the same value for different other atoms, so that is for that case, that is for helium plus or lithium 2 plus 1 electron system, the system need to be 1 electronic, remember this one. Then En should be proportional to Z square by N square, because for different systems Z should be different. And along with that, you can multiply E1, that is the energy of hydrogen atom, the first orbit of hydrogen atom. Okay, because the other parts are constant, so you can get that value. So if you put the E1 value, then you will get energy of any orbit. Okay, so this is a little bit tricky, but it's quite amazing. So now I have got the energy values, I have got the energy equation. Now I have to put the energy equation to calculate to get the spectral properties. So okay. So suppose a thing like this is the orbit and this is another orbit. So when electron jumps from this orbit, that is Ni orbit to Nf orbit, that is Ni has the much higher distance, that is it has the higher energy values. So when electron jumps from Ni orbit to Nf orbit, then some amount of energy will be released by the system. Okay, so that energy we will get in the spectral form. Okay, that I have told you that we will get the spectra. Okay, and we can explain the spectral properties. So as Ni has higher value, I have told you that you have to subtract the lower value from the higher value. So that's why I am subtracting the value Ni minus Nf, energy of Nf, and that energy difference should be equal to h nu from the both postulates. So just put the energy value from this equation. Okay, then what we get, this value, and the variable is Ni and Nf. So just we will get this kind of equation. After organizing this equation, we can get this value, and then let the h to bring the h over here. Then nu equals to that c by lambda. So bring the c over here. Okay, transfer its position. Then we will get 1 by lambda value, that is called nu bar. That is the wave number that we call wave number. That is equals to this. So I just organize the equation. So pause the video and do it yourself. You will get the same equation. Okay, I have done in the SI unit over here. Okay, you can do the same in the CGS unit. Okay, so just change the energy equation. So you will get the equation in the CGS unit. So here the term except the Z square term, the term that present Am e to the power 4 by 8 epsilon naught Ch3, that is called R. Okay, this is a constant that in the next time we call it Rydberg constant. So this is the equation that explains the Rydberg equation. You know about the equation already, right? So the Rydberg constant, if we put the different values, if you put the m value, mass of electron, charge of electron, epsilon value, c, light speed in vacuum, then h Planck's constant, then you will get in CGS unit the 109700 centimeter inverse, and in the meter unit SI unit 10970000 meter inverse. Okay, so getting all these values, and finally if I have already told you that I have got this equation, and the R value in SI unit is this and the R value in CGS unit is this. So to get the R value you just need to put the energy value in the CGS units. Okay, so you can, if you put that value you will get the R value in CGS unit. Okay, so till now we have got the radius equation, we have got the velocity equation, we have got the energy equation. I have put the values in the CGS unit over here, so you can do anything. So I am let me tell you that you should do the calculations in the both CGS and SI units. So I have shown some CGS units, I have shown the SI units, and I have told you that how to do that. So do it yourself, because that will help you a lot when you apply your concept. Okay, because you need to learn how to play with units, because there is a lot of units over here, so you need to learn that. Okay, so do that in the CGS unit and check and verify that whether you are getting the same equations or not, whatever I have provided you, okay, in this slide. So after getting the different Rn equations, so first one, in the first case I have told you 1, that means for hydrogen atom. Okay, so if you put the n value, that is the for hydrogen atom there is only one orbit, so if you put 1, h value z equals to 1, so you will get 53 pm. For helium plus atom z would be different, but for first orbit for helium atom n equals to 1. Okay, that means for hydrogen atom z equals to 1, so the full value divided by z. Okay, because putting z or ignoring z, both will give the same result. So for helium atom you just have to divide it with 2. For lithium 2 plus atom, 53 divided by 3, only vary the z, right? So here you can get all the different radius. Okay, so just pause the video and learn what I have told you again. Okay, so that's quite easy. So next, I have told you in the first video that I will be talking about alpha, beta and different gamma lines. So first listen one thing, that we have got different series: Lyman series, Balmer series, Paschen series. So for Lyman series, alpha, beta, gamma, delta, different lines are possible. For Balmer series, alpha, beta, gamma, delta, different lines are possible. For Paschen series, alpha, beta, gamma, delta, different lines are possible, and so on and so forth. For other series also, alpha, beta, gamma lines are present. So for each of the series, we can have alpha, beta, gamma lines. So how? So for Lyman series, suppose emissions, we are considering the emission spectrum. Okay, that means from higher energy orbit, electrons come to the lowest energy orbit, lower energy orbit. Okay, so for Lyman series, the electrons need to come to n equals to 1 from higher energy orbit. So when electron comes from n equals to 2 to n equals to 1, so the difference would be 1. We will get alpha lines, alpha Lyman series. If electron comes from n equals to 3 to n equals to 1, then we will get beta Lyman series. When electrons come from n equals to 4 to n equals to 1, then gamma Lyman series, and similarly from n equals to 5 to n equals to 1, delta Lyman series, and so on. Okay, so for Balmer series also, so Balmer series electrons need to come to second orbit from higher energy orbit. So from third orbit, that is difference, when difference is 1, we will get the alpha line. When difference is 2, that is from 4 to 2, fourth orbit to 2 orbit, second orbit, then we will get beta Balmer lines, gamma Balmer lines, then fifth to 2, likely to be same is as the previous ones. Okay, so this Paschen series is also same. So I think that you have already learned that how to get the alpha, beta, gamma lines. Okay, so now let's do a lot of corrections. So why correction is needed? Because in the Bohr equation, Bohr was the first one who explained the spectral properties and the atomic model. Because what Bohr did, Bohr explained in most of the cases, Bohr explained Bohr gave the exact value, exact explanation for the stability of an atom, and the all the things are verified. And the second case, Bohr gave the exact Rydberg equation. Okay, so there was something, and we know now that the something term is the atomic number square. Okay, so Bohr gave that term also. So that's why Bohr theory is quite successful. But a little bit correction is needed in the Bohr theory, that when we got the Rydberg equation, so we are just if you put the value of R, then you will get the equation like this. Okay, so this M. So here we are getting the M. So actually when we consider the M, that means the mass of electron. But actually we cannot consider the M only, because when electrons are revolving, not only the electrons are revolving but also the nucleus is vibrating, because when it's of classical mechanical things that little bit electrons should be, nucleus should be little bit vibrating, but we thought that nucleus is fixed in its place, but that is not true. So as nucleus is vibrating, so nucleus doesn't have a fixed position. So that's why we need to take another concept, that is of rest mass. So rest mass means mass of electron multiplied by mass of nucleus divided by mass of electron plus mass of nucleus. So we just need to put the value of reduced mass in the place of m. So put the value of the reduced mass in the place of m, mass of electron, and you will get the same equation. So this is more accurate equation than the previous one, but whenever you will do the normal calculations, just use the m. Okay, so it's the correction only. Okay, but don't use this equation if you are getting a lot of problems to you when using the Rydberg equation. Just put the value of m, not the reduced mass, until they told you that to use the reduced mass. Okay, so I have told you the Bohr's theory has explained a lot of things. Okay, so a lot of merits are present, a lot of demerits are present. So let's talk about merits, what Bohr theory suggested and what Bohr theory explained. Okay, so first, the stability of atom. Bohr theory explained the stability of atom, and finally what we get, that in the Bohr theory can able to explain the stability of an atom. How? Because when Bohr told that when electron is revolving around the nucleus, it is not releasing any kind of energy. Okay, so and it has some kind of some stable orbits, some stationary orbits. Okay, so that's how Bohr was able to explain the stability of an atom. The second one is the prediction of frequency of spectral line. So Bohr has from Bohr theory we have got this one. Okay, so this is nu bar, that is 1 by lambda. So if you know the lambda, then you can get the nu, that means frequency. So nu equals to c by lambda. So multiply with c the value of nu bar, then you will get the frequency. So Bohr theory exactly explains the frequency of spectral line. Then Rydberg constant. So from experiment we have got the Rydberg equation value is this, and if you calculate, if you put the value m, e, so do it yourself, I am giving you as a homework. Put the value of mass of electron, charge of electron, epsilon naught value, CHQ, then you will get what the value, and that value will be very close to this experimental value. So that's why the experimental value is quite close to the value what we are getting from the Bohr's theory. So that's why also Bohr theory was quite good. Then we can calculate the ionization potential from Bohr theory. So we will learn how to calculate the ionization potential from Bohr theory, right? And next we can explain the Bohr's correspondence principle. So Bohr's correspondence principle is also quite important, right? So we learn what is Bohr's correspondence principle. This is the advanced quantum mechanics things. Okay, but I will let you understand that how to understand that one. Okay. So next, a lot of demerits are also present, that Bohr theory could not explain these things. Like Bohr theory mixed up the classical quantum mechanics. I have already told you about that. Okay, that Bohr theory has some concepts of classical mechanics and has some concepts from quantum mechanics, like quantization, like things. Then Bohr theory cannot explain the fine spectrum. So why fine spectrum? So see these demerits, that Bohr theory cannot explain the Zeeman and Stark effect. So what is fine spectrum? Suppose you have got one line, that means like this kind of line. Let me show you. Yeah, so you have got only this kind of line. Okay, this kind of line, or this kind of line, this kind of line. Okay, but both, what happens if you are getting this kind of line, then from the low resolution image, you are just watching, you are just seeing only one line. But if you put that system, that means that atom for which you are getting one line, if you suppose that's the hydrogen atom, so if you put the hydrogen atom in the magnetic field or electric field, then that spectral line will be divided into different fine spectrum. That means a lot of spectral lines are hidden in that single spectral line. So what we are thinking about, that was only one line, but actually that is made of a lot of lines. Okay, so those lot of lines are called fine spectrum. So Bohr was not able to explain the fine spectrum, Okay, so if we got the fine spectrum in presence of magnetic field, that is called Zeeman effect, and if in presence of electric field, that is called Stark effect. So Bohr could not explain the Zeeman and Stark effect, which causes the production of fine spectrum. Okay, but again, another demerit is that Bohr, I have told you that Bohr theory is only applicable for one electron system. So more multi-electronic system, Bohr theory is not available. Bohr theory is not good. Bohr theory doesn't give the exact result. Then Bohr theory doesn't obey the Heisenberg uncertainty principle. How? So suppose I have to, let me show you the picture first. So according to Bohr theory, electron should revolve around the nucleus in a circular orbit. So if electron is present over here, then electron should no electron, if we can, as it is the product of both classical and quantum mechanics, so we can exactly determine at any moment, at a particular moment, we can exactly determine the position and the momentum of a electron. Okay, so from Bohr theory it is possible, but according to Heisenberg uncertainty principle, which is much more prominent, which is very acceptable and very successful principle, according to that principle, that is not possible. At any moment you can calculate, you cannot calculate both the position and momentum, okay, in a single moment. So that's why Bohr theory is not that much doesn't satisfy the Heisenberg uncertainty principle. Okay, this is another demerit. Again, Bohr theory of quantization of angular momentum. So I have told you that, I have shown you that in the postulates, the first one is mv equals to n is by 2pi. So where Bohr told that n is an integer only, but Bohr couldn't explain the significance of n. So why, what does the n signify? What does the integer mean? Bohr didn't explain that. And finally, you know that n is the principal quantum number. Okay, that now you know, but at that time Bohr did not explain that one. So that were some of the demerits. So now let's talk about some other things like ionization potential. That is a very important topic because a question came in IIT examination. Okay, so listen carefully. So you know what is ionization potential. So in ionization potential, you can define this like a, so the element, any element, for to calculate the ionization potential for any element, that should be in gaseous state, and that element, suppose there is an electron in the valence orbital. So if you remove that electron and take it to infinity distance, okay, then from a valence orbit to take it into a infinity orbit, infinity distance, you need to do some work. Okay, so that work is called ionization potential. What amount of work, what amount of energy you need to provide, because here is the electron, and if you need to take this electron to infinity, so positively charged particle nucleus will attract the electron. So to take it to infinity, you need to do some extra work, you need to do some add some energy, so that electron accept that energy and it goes to infinity. Okay, so you need to give some energy in the system. Okay, so that required energy is called ionization potential. Okay, to take the electron to the infinity. Okay, so I have told you that if the distance increases, the energy of the orbit increases. So let's say that the infinity, the orbit, okay, the orbit will have the infinity, n equals to infinity. So n equals to infinity should have higher energy than n equals to 1. So you need to subtract the n equals to 1 from n equals to infinity. Okay, higher energy orbit to lower energy, higher energy orbit to lower energy orbit. So just put the value of infinity and 1, so you will get the equation. Okay, and finally if you put all these values, as we are calculating this for different systems, because I have put only one electron. If you put the only one electron system, so except z, everything will be constant, and here also it's true. So just 21.8 into 10 to the power minus 19 into z square joules per atom. So if you convert this value into joule to electron volt, then 13.6 into z square electron volt per atom. This is for hydrogen atom. Okay, and just for hydrogen atom you can put the value z equals to 1, so you will get 13.6 electron volt per one hydrogen atom. So if you want to get for helium atom, helium plus system, then you just have to put 2, lithium 2 plus, you just have to 3 square. Okay, so and so on and so forth. So for one electron system this is 2, and for if you need to calculate for poly-electronic system or multi-electronic system, then you need to use a different equation. Okay, so that is, I am not explaining this equation, that how does it came. but just remember this equation. This is very important, and one question came in JAM 2015 or 16 using that equation. So just put Z here. I haven't put here just only Z value. I have put only the Z square value, Z star square value by n square. So n is the the number of orbit, okay, where the electrons came. So you can ignore that one. But Z star means, okay, so if you need to take the electron, suppose in the question they are asking about from third orbit to infinity, okay, what are the energy requirement? So n will be 3. For fourth orbit to infinity, so n equals to 4, like that. And that Z star is called effective nuclear charge. That means Z minus screening constant, okay. So effective nuclear charge I will discuss in future, okay, in the periodic table chapter or in this chapter later on. But now I am not discussing that how you can get the Z star value, okay. So just keep watching this video and until I make a video on Z star, how to calculate the effective nuclear charge value. So this is the formula for polyelectronic system. So if you know how to calculate the Z effective or Z star value, then you can use this equation from any orbit to infinity, okay. So how the energy requirement for polyelectronic system, okay. So for if you use the equation for hydrogen atom also, then you will get this value, okay. So this equation is the fundamental equation and this equation is the universal equation. So this equation you can use for the hydrogen atom also. So just put n equals to 1 and Z star will be Z for hydrogen atom, because there is only one electron for hydrogen atom, okay. So next another principle was there, that is the Bohr correspondence principle. So listen, according to classical mechanics, as Rutherford said that energy released by the electron will be continuous. So if the electron releases its energy continuously, so we will get continuous spectrum, okay. That means we are not able to get this different line spectrum. We can get the spectrum like, let me show you, this continuous spectrum. We won't be able to get this kind of different lines, okay. So in Bohr correspondence principle, what happens when n has a value of infinity, okay. So n is a value of infinity, then energy requirement will be very high, okay. So in that case, suppose n is infinity, that means suppose from the nucleus the distance of the nth orbit, that is infinity orbit, will be infinity. So as the distance is very high, that means you can think that from the nucleus the distance is very high, that is a macro body. The system is a macro body. Take it as a ball. So from the nucleus, from the center of the ball, billiard ball, from the center of the ball till the radius of the ball, so you can take that radius as infinity. So you can take anything at infinity, okay. So that's why if you go from the nucleus to the infinity, then you will get a macro body. So macro body, that in case of macro body you can apply classical mechanics. So for larger values of n, you will get the same result from classical and quantum mechanics. That means for larger values of n, classical and quantum mechanics lead to the same result, and classical and quantum mechanics merge, okay. So and we will get continuous spectrum for larger value of n. So this principle, that for larger value of n, classical quantum mechanics they generally provide the same results, okay. So for this principle is called Bohr correspondence principle, okay. So I will be discussing this concept in the particle in 1D box in future, in the quantum mechanical discussion in this chapter, of course, in these video lectures, okay. So I will be discussing that one in the later on, okay. So now the last thing about in this session is the atomic unit. So this will not be necessary for you till now, but when you learn the advanced quantum mechanics, then you need to know what is the atomic unit. So mass of electron, you need to know that mass of electron is this radius of first Bohr orbit, that is called Bohr radius, okay. So for hydrogen atom, what is the radius, the first radius R1, that is called Bohr radius for hydrogen atom, okay. That is 0.53 Armstrong. The charge of the electron is this coulomb. Energy is like that. Length of the first Bohr orbit, that is this one, okay. 4 pi epsilon naught value. Velocity of first Bohr orbit, okay. Velocity of the electron which is present in the first Bohr orbit, okay. The value is something will be the value if you calculate the value. Then the time, how much time it will take when it revolves a complete time, okay. When it takes a time, okay, to revolve it. So that time is there should be a particular time. But if you take all these different values, the quantum mechanics will be very complicated, the advanced quantum mechanics will be very complicated. That's why the mass of electron is 1 atomic unit need to take. Okay, so these are called atomic units. Okay, so we need to use the atomic units, and in the atomic units, the mass of the electron is 1 atomic unit, radius of first Bohr orbit or Bohr orbit is 1 atomic unit, charge of electron is 1 atomic unit, energy of electron is 1 hat 3 or 1 atomic unit, length of first Bohr orbit is 1 atomic unit, 4 pi epsilon naught value will be 1 atomic unit. So you just need to put the value of 4 pi epsilon naught equals to 1. Velocity of first Bohr orbit is the electron of the first Bohr orbit is 1 atomic unit, and the time required to do a complete revolution in the first Bohr orbit is, in the first Bohr orbit means time 1, that 1 means first Bohr orbit is 1 atomic unit. So all the values will be 1, okay, according to the atomic unit, and put the value in the we will use these things in the advanced quantum mechanics whenever we will discuss in future. Okay, so that's all about the atomic units. So I think I have discussed all the things whatever are necessary, okay, to qualify the IIT JAM examination and to clear the concepts, and I have told you the story behind all those, okay, what was going on in that at that time in the scientific community. So I think that is quite enough, and that's all about this video. And if you want to prepare for IIT JAM examination, you can visit this website, and if you want to get the study material, you can visit that website, or you can WhatsApp me, or if you want to join the IIT JAM Chemistry 2021 Chemistry WhatsApp group, you can also get contact me. Okay, I will be adding you, and there are certain instructions, certain conditions to join that group. Finally, I have completed the Bohr theory, and in the next section I will be discussing another one, and finally we will go into the quantum mechanics, and we will be discussing a lot of things over here. So that's all about this video. Thank you. Thanks for watching.